Okay, so that conclude the connectivity. So after that, when you set up like the way you want to manage the connection with the UT, is like we're going deeper as the test benches itself. So the test bench is the more static part of the setup. So where you have wiring, conditioning for some signals, and like actually really thinking about the bench ergonomics. So I will allow Alex to talk about the test benches that we and all
Yes.
the important parts.
Yeah. So here I wanted to show some example. The one on the left is one that I've shown previously, but you can see that test benches can be of different forms. The one in the center is a 24U rack. So basically, it's about like a meter and a half tall, perhaps a little bit less. So depending on the configuration and the space that you have, we can adjust the different test benches to be able to fit inside your space requirement. Like the one on the right, completely on the right, is an example of an introductory test bench that has a generic test bench approach with the simulation on the left and all the loads and the controllers on the right.
Mhm. And one quick fact I can see there is like the one on the right, actually, if you see there is actually no connection on top. So all the connection are done internally of the racks. This
Yeah.
is due by the fact that the controller itself, like like the VPC chair that we're talking about on the right, the farthest right side,
Yeah.
like the all the connection are done internally. But if you look at this one in the middle, there's a lot of connection in the front. This is because the customer require like a smaller rack for all these reason, and actually probably his controller is on a rack next to it, which he will provide. So his requirement was to put all the connection in front. So like the wiring to the UT in this case was really done in front of the rack itself. And on the left is like a kind of a mix. Like we don't have a lot of connection, but actually we have control panel in top. Like we have like I know this bench, but there's some dial there to actually inject some condition to the unit under test. So really, like the design ergonomic of the bench will change accordingly to what you want.
Yeah,
A lot of
precisely.
thing we saw is like usually like if the UT is internal of the bench, the connection will be internally, but sometimes you want some port, like maybe like if you have a CAN bus, for example, you want to pass a CAN bus and have a connection in front of their benches to actually maybe have an external tool to monitor the bus from a laptop PC, which is not part of the real-time systems, but like really to just for monitoring to see what's going on in there. Mm.
Yeah, no, for sure. That's a point that will be discussed a little bit later also on the IOs. But one thing that can be said so far and is one of the most important is we need to recall that it depends on the test that you wanted to do at the beginning and how you want to set up everything. When you were planning everything with your EICD, what type of benches that you wanted, it's all where you're going to define basically the interaction that will be done with I'll call it the external world, which is basically the controller with the simulator and everybody in the lab. So some of the general design rules that we learned throughout the years. Right now, what we've seen for the wiring, and it's basically like not orders, but it's basically a good rule of thumb to recall. So take a habit of wiring spares because it doesn't seem like it at the beginning, but you recall when I was saying that your controller was in R&D phase and that um, it's not completely fixed the design, and you see that R&D adds a set of new sensors in it, but you're at the end and the cables and everything has been done, and you need to add like 4 wires outside of everything. It becomes really a hassle. But if you took for yourself to actually do the wiring of the spares, it might just be coming to add the pins and insert them in the connector because there were flying leads, for example. Uh, Another rule of thumb is a lab test bench is not an airplane. So don't overspec. Why is that? It's because at one point, some of the customers were requiring the exact same shielding or the exact same functionality as in the airplane, where the noise is obviously way more present than it might be in a standard lab with a controlled environment. So keep in mind where your bench will be, because it's not necessarily critical to use Teflon isolated wires, which cost 3 times the price of a more standard sleeved wire that would do the same job. So you can save onto that if you don't overspec. Wire color coding, not everywhere. If you've seen a little bit in the aircraft or helicopters, usually they mostly use white colored wire. So as the technician that will do the maintenance will actually pay more attention to the signal that they will be monitoring or correcting, instead of just going color coding, and that the color code, there was an error at one point, and they just go by the code. But in your test bench, depending on where you are, it might be actually interesting to color code, because if you want to have like is shown here, it's an interconnection box. Inside the box, you might want to be able to do some quick validation or quick correction. So having it color coded might be a good idea. But then again, think about it and use it carefully, because it might have an impact that people may take for granted, that the color will be a certain type of signal, and not really validate on the documents and the design sheets. Adjust cable length to prevent tension. I'm pretty sure everybody is fond of guitar sounds, but whenever you have a harness, a cable in your bench that is the tension is enough to make it sing, usually it brings damage to the cable during the time, the lifespan of the bench. Recall that those benches are supposed to last 10 to 20 years. So give yourself some room, give some space for the wiring, so that way it won't get damaged by undue tension on pins on the connectors. Also, size does matter. Wire bundles can get pretty big. So if you take a look at the blue wires inside the box, you see that a few together will be pretty thick. So the arch in which the circumference of the cable will be able to do will be lessened concerning this. And also you need to keep in mind that all those wires need to go from one box to the other, and all of that needs to go in the end to the controller that you want to test. So all those wires need also to be accounted for space-wise in the bench. So keep in mind that your cabinet need to be spaced accordingly to be able to support the wiring schemes. Next slide. So the signal conditioning, each simulation platform, be it by National Instrument, OPAL-RT, or any other, they all have their own set of generic I/O that is readily available on top of the counter, super easy to find, super easy to use. The issue here is that usually most of those I/O cards are not necessarily set to replicate the IOs or the systems, the subsystems that will be used and connected to your controller. So this means that you need to account for signal conditioning to adjust the level of the voltage, the current, or add some resistance values inside of that. So technically you will always have a need for conditioning modules, but you need to take into account that most companies already manufacture a lot of those. So rest assured that you don't necessarily need to go on a design spree and reinvent the wheel. A lot is available on the market. So keep your eyes peeled. You'll be able to find what you need. And again, always keep space for upgrades because, like I mentioned again, your R&D controller will probably be evolving and you'll need probably more space than you accounted for at the beginning. So it's always a good rule of thumb to account for that. So the modular loads, so basically what we can see on the left are actual motors or position sensors that are on the airplane. So in this specific case, it was for an R&D bench. So it is possible to integrate them inside the bench. But sometimes, like I mentioned, you may need to step it down a notch. So because you won't be able to send, I don't know, torque motors to all of your distributors or all your providers. So you want to go with something more less involving. So for example, potential meters, simulate the, and with an air compressor, the altitude, for example. So to make it easier to work with the bench. Um, One of the concerns that you need to keep in mind, though, is that certain type of loads may induce noise, vibration, use a lot of space. Sometimes also you'll have like real life current that are, let's say, in the 1,000 amps. But does your controller really need to have 1,000 amps in the bench, or can we just crack the ECU and connect to the sensor itself and bypass that LEM sensor that actually reads it to be able to replicate it with a cheaper solution, but also with a much more easier approach because you won't need any safety issue to work in the millivolts instead of 1,000 amps. So one of the questions for bench ergonomics that you have to think about is where do you plan to install your bench? Will it be a room with no AC? We've seen some places in India that it's actually almost outside. So you need to think that you will need to add perhaps some cooling inside the cabinet to take into account that the ambient air will be high. Will your room have rugs? Um, Yes, we've seen it. So in those specific conditions, what we had to do is actually integrate more grounding. So grounding bracelet for the staff that will be working on the bench and more grounding on the rack and some specific approach also that you needed to touch the frame to be able to be grounded first before touching anything. So those type of things do happen in real world. So you need to account for it. Will the room will be on an uneven floor because you're an old building? Well, you might want to have lockable casters, so wheel that can be locked on the cabinet to prevent it from moving, for example. Well,
Yeah, I
yeah.
remember a room once that it was pretty much even, but there was like one step to enter the room. So like bringing the bench to this room was kind of a nightmare.
Exactly. And this brings me for if it's outside on a tarmac, we have also ruggedized type of cabinets. So perhaps also like a multitude of smaller boxes will make more sense also if you have to go to a step or go somewhere else. Also, do you want to probe on the ECU often? If yes, you need to procure a space to be able to put your hands and be there. And will it be right beside it for an extended period of time? Like I mentioned, some of the equipment might be pretty noisy. So sometimes you might want your cabinet to be noise proofed with sound deadening to prevent your ears after 8 hours of being sitting right beside a stepper motor. Let me tell you, your ears will thank you if you add sound deadening to the cabinet. So fun facts, some of the benches weigh more than 600 kilo, which is basically 1,200 pounds. So plan for it because it's going to be on a square meter or perhaps like 9 square feet. Sorry. So you need to be able to make sure that your building is able to support such weight. Uh, some standard cabinets are not sized for standard office doors. So pay attention to spec your size accordingly to where they need to pass through. Again, like Mathieu mentioned, there was like a one step. We've seen some customer that had to bring it to the second or third floor without having any um, elevators. So in this case, they had to completely disassemble the bench, bring it up, and reassemble it. So it's a bit of a pain. So you may need to think about it before. And some benches may need more than one breaker circuit. So if you plan to connect all of that into one 50 amp power line, well, maybe you need to think again and think about it, because some benches may require even high power three-phase outlets.
Thank you, Alex. Uh, we hit a point where actually the webinar actually was planned for 1 hour. I think it will go a little bit more than that. Sorry about that. Like as usual, I think was kind of expected as well. So I will try to go through all the next elements with a faster pace. But I just want to remind you that we have a question period at the end. So we have time on our side. So if you want to stay and ask questions, we'll be there as well.
Yeah.
So next thing is like the real-time platform. So really the real-time platform is really like the center of the test bench. It's really like the brain. Like this is what bring the test bench up to life. So when we talk about selecting your real-time platform, what you need to ask yourself is like, first, typically you want a real-time performance, but sometimes it's not that clear. Like depending on where you are in your testing or like your test synopsis, sometimes you want something to simulate the bench, and this is what we call usually like open loop. So you have a function generators that do enough functionality to generate signals to simulate the bench and actually like just do point-to-point checkup on their controller to see if they saying the right thing. For example, setting a signals for pressure. So like if I'm setting this voltage, do I see the right pressure or maybe temperatures? But there's no closed loop interactions. What real-time simulation bring you is like actually dynamics between the unit under test and the simulator. So now you need real time. So you have a real model of dynamics where the all signal acquire will have some reaction to send back information to the UT. So basically, you have like a command to change altitude, and they actually like there will be a ramp, but it will not be as steep, but it will be like a smooth transition with the mathematical models. This is done in real time. Keep in mind that when you have real-time capability, open loop testing is easy. But if you select a platform that doesn't really have real-time capability that much, you will have a hard time to go to this real-time capability after that. So plan accordingly. You want also a platform that have like the IO set that you want. It's actually really common that we take the standardized IO and we do some conditioning in the test bench. Actually, this is like happening all the times. But when you select your platform, make sure that you have enough IO or IO that makes sense to start with. Same thing as communication port, like the communication from the simulator is mandatory because this is where it all starts. So like make sure that the platform that you choose have an efficient way to make those communication. And also you want to plan for the future, so you want some upgradability as well in your system. So could I add like some more communication buses or IOs on my simulators? Are the performance are good enough to be for the future as well? So if we go to the real-time capabilities of a system that you're choosing, actually you want two things on our point of view. You want like to run the simulation on the CPU. This is the faster way to achieve real time. So you take a C code, then after that you compile that to a real-time platform on multiple CPUs. So basically you want a system that support more than just a single CPU. Even if today like the CPU are getting faster and faster, so you don't actually you need less and less parallelization on this on the cores, but still having this flexibility is always optimal. and you're looking for the performance that going to fit your needs. Typically, like the performance, like we're looking something that can achieve easily 100 microseconds for like a good size models. Okay. So far in my previous life, I see that lots of simulation run at around 1 milliseconds to 5 milliseconds for the aerospace industry. But more and more, I receive demands to go faster than that. I would say like 500 microseconds. But if you find like platform that can give you 100 microseconds and more as performance, you will be future proof, I would say. Then next to that, like you have a high performance, but you need like FPGAs a lot of time because you have some concept of signals where the 100 microseconds, for example, won't be enough to generate signals for your systems. But like the thing is like the triggering could be from the CPU, but you need like DSPs or FPGA to actually like do higher level kind of signals. So basically, if you have a magnetic pickups, you want maybe to record these patterns that you know that exist, and actually you just trick this the FPGA to reproduce this pattern at different speed. LVDT or an RVDT are some component that need to be simulated on an FPGA because they have a carrier, they acquire the carrier signals, and they're just like adding an amplifier value to that as well. Same thing at resolver. So like really like the platform that you choose need to coordinate the CPU with the FPGA. Also, something is really tricky is like when you have an FPGA, make sure that the FPGA is actually connected to real IOs and not just short of. Because if you have an FPGA and you're stuck to like all digitals and you need like to send analog signals, like it's achievable, but it's harder. If you have an FPGA that actually add the flexibility right now to have like a good mix of type of signals, that's help a lot on the architecture as well. And make sure that the FPGA is not closed, that you have access to that. So if you want to add your own process to that, like the supplier have to provide you an SDKs for the programming that in their environment. So if you look a little bit like what is look, so basically you have two paths usually of programmation, and at the end you want the platform actually that bringing you like a coordination between the CPU side and the FPGA slash DSP. Uh, so for your platform as well, you want them to support a lot of IOs. So typically you need analog and digital IOs as an entry and a output. Then after that, you look at the specs, like are they able to provide like enough voltage range? Like for example, OPAL-RT is plus or minus 16, but typically what we see in the industry is plus or minus 10 volt. You need to see that to also look at the precision is makes sense for you. Um, Something you need to look as well is the current that an analog output can sense. Like since you go through a benches with many connection connectors, if you want like an analog output that can push kind of a good amount of current, like maybe like we're talking about milliamps, but like maybe like more than 1 or 2 milliamps, because you don't want reflection in your cables. Same thing as output, like uh, usually people would provide like a different output, like but you want a mix of output that maybe are like really fast as TTL1, but if you want to drive a relay, for example, which is really common, if you just have TTL digital, there's not enough current to drive like a mechanical relay. So maybe you want also a set of digital output that have enough powers to drive a smaller relay. So this is consideration that you have to ask yourself on the IO type. There's also like all the connection about the IOs. Like, is it efficient? Is it easy? Like, is it like well organized? Is it something that I can manage internally if I want to add something as well? Like, do you have the tool set to make the connection to the systems? And you know, like we're always susceptible to have like some issues. So all the IO are have some maintenance. Could you swap them? Let's say you burn some channels. Is it easy for to be changed on the field as well? That's something that you have to take in mind. If you look at the communication, So like the wider set that you have for aerospace communication port, the better it is. So what we usually saw in communication is like the iRing 429 is like a something really fairly common in the industry. The MIL 1553 as well. AFDX more and more for sure. Uh, like it's not communication, but like the thermocouple, the PT 1000, PT 500. So like those things they need like a special cards. CAN for sure. Like I almost see CAN in all the aerospace industry as well. We see a little bit more TCP/IP as well, like more and more like some accessories around the ECUs. But like it's up to you at the definition of your project to make sure that the simulation platform have all the right communication for you. It's always important as well, like from my previous experience, we have customer that actually is not related to the ECU, but they want the bench actually to talk to a mainframe, like a main controller in the lab. So when they, especially in Nuremberg, I have like some really neat customer that they built an architecture where they have like a central controller PC and they define like a bus where they can control all benches. So all supplier of benches, they require they talk to this communication port. It was actually TCP/IP with like a predefined packaging. And from there, like the main can actually start the benches, change parameters, and controlling the benches remotely, which is really needed during test sequence. So basically, in this case, like OPAL-RT, we build the protocol actually with just a C code over TCP/IP, which is not that difficult. But like having this flexibility in your hardware, like your simulator, is really important.